Humans have always had the impulse to explore towards the night sky, towards the cosmos, towards the unknown.
Thrusting outward into space, we gain new perspective on ourselves.
But it's not just about going as far as we can. Space exploration also provides a unique vantage to look back at Earth, all of Earth, in near real time.
Exploring space, we learn quite a bit. We learn about our home planet, we learn about our solar system, we learn about our universe.
Sensors on satellites have revolutionized the way that we understand the Earth. The data is used for measuring snow cover, infrastructure in cities, mapping. There's a lot to explore.
The technology has increased in capability, has decreased in size and cost, and that enables a lot of things to happen.
I'm Krajnovic.
And I'm Myrna James. It's time to go behind the wings. A big focus for NASA and players throughout the industry has become our own planet Earth. So today we're going to focus on the question, what can we learn about Earth from data from space? To start, we'll talk with Dr. Kate Calvin to learn what NASA Earth is all about.
One of NASA's most important missions is our home planet, Earth. And we have a lot of research going on about Earth, from observations to models to technology. We measure the Earth on and above the Earth's surface, so we can see the state of the Earth and how it's changing. We build computer models that help us understand Earth. They can both help us understand the processes that are impacting Earth. They also give us a window into the future so we can see how Earth might change going forward. So you think about some of the pictures that astronauts have taken from the Apollo missions or from the International Space Station, and you see Earth. You see this beautiful blue ball with clouds swirling around. And our satellites help us take those sorts of images nearly continuously and looking at all of the Earth. Each satellite is designed to measure something different. So some are looking at visible light, some measure changes in gravity. And we have more than 24 of these satellites and instruments in orbit. And together they let us see things like vegetation, carbon dioxide, clouds and precipitation, changes in the mass of ice sheets, and much more.
The satellite era in the grand scheme of Earth science is relatively recent. Started just after the launch of the Sputnik satellite in the late 50s. Into the early 60s, it was very experimental. There was a lot of funding for developing rockets and thinking about how to put people up there. In terms of the instruments that could view our Earth, that was a little bit secondary. Well, the first cameras that went up were analog. Film canisters were dropped from space down and being collected by people. Into the 70s, then digital technology started to come online, and that was really exciting because it allowed us to start to do some really fancy things like send out microwave signals with timestamps on them, which we use to power our global positioning system, or GPS network. Right, so we've come a long ways as Earth scientists in the use of satellite data. Right now, it's indispensable. It's difficult to imagine how science would be undertaken without satellite instrument measurements.
We've been collecting observations about the Earth from satellites for decades, so we can see not just the state of the Earth today, but how it's changed over time. One of the satellite programs that we have in partnership with USGS is called Landsat. And Landsat lets us see land use and land cover. So we can see where there are forests, where there are urban areas, where there are crops or snow. And we're coming up on our 50th anniversary of Landsat, so we have nearly 50 years of observations of land use and land cover. So we can see how that has changed over time. And when you look at Landsat records, what you'll see is expansions of urban area. You'll see declines in forest in parts of the world. And we have other satellite missions like that give us different information. And we work with a lot of the commercial partners. So we actually have a commercial smallsat data acquisition program where we buy data from some of the commercial smallsats and make it available to NASA researchers so that we can do more climate research, more Earth science research using other satellites, not just our own missions.
Satellites are constantly orbiting the Earth, and you probably use them every day, whether you realize it or not. We're about to use GPS, or the Global Positioning System, to head to Maxar's headquarters. We're going to meet with Dan Nord to learn more about satellites and their sensors. What can we learn about the Earth by looking back at it from space?
We think about that every day, and the answer is a lot. And so we have an ability to look at a holistic scale at the world and monitor change. And since we've been doing it for 25 years, we actually have change over time. And with that, you can model a lot of behavior. And then if you look globally, it's, where's the next big city growing up? We can answer that. The life cycle of a satellite is fascinating. And first, you need to figure out what you want to do with your satellite. And so we make high resolution Earth imaging satellites. We also make satellites that help with communication, whether it's Wi-Fi or other, and then multispectrals. And then you have to build a satellite, and this is the hardest thing. This is more like building a Ferrari. This is custom built, hand built, large scale technology that cannot fail. You can't go fix a satellite once it's up. There are some companies starting to think about how to do it, but the thing's moving, thousands of miles an hour far away. So everything has to be checked, double checked, and quadruple checked.
So yeah, let's take a look at the satellite. It's got a couple different parts here. I mean, on the sides, I know you said satellites don't have wings, but what's happening on the sides?
Those are solar panels that brings in the sun's energy to power the vehicle, but this doesn't have wind resistance or anything. Solar panels can't fly.
They're not going to provide lift.
And then if you look up here, this is the camera. So this is actually inverted, aiming down at Earth.
So we have our power source, this would be our sensor, and then I imagine somewhere on here is a communication device to actually transmit that back to Earth.
There you go. Yeah, and so it's flying, taking pictures, and in real time sending the data down to our ground stations. And you've seen, what a generic ground station looks like. It's a dish looking straight back up. Space is hard, and what it's reflecting is just how complex building machinery that needs to withstand extreme temperatures on the hot side, extreme temperatures on the cold side, radiation. There's so much you have to protect against, and it has to work every time. You then, pick who's going to launch.
There we heard the final call. LD is go for launch.
And we have liftoff.
The last one we did for Sirius XM was on a SpaceX rocket. And then once it's up, they put it in the orbit that we ask for, either low or mid or high. And then we take about a month to get it into place and test every single element. And once that's done, we start pulling imagery down. These are big imaging satellites that can capture all of Denver in one pass, but then can zoom in and look at an individual vehicle with enough resolution to know what's the make and model, which is incredible. And then when it's time to decommission a satellite, you put it in a drag orbit and it burns up in the atmosphere.
Over 4 billion people are using Maxar technology every month. People are probably interacting with satellites whether they know it not on a daily basis.
The way mapping works in the old days was you had to physically go to a place, and even Google, when they did their first mapping, they drove cars all around the world, whereas a satellite can do it relatively quickly.
I do want to focus in a bit because there are so many examples. Tell me about the work you do with the Jane Goodall Institute with chimpanzees and mapping and conservation.
From space, we can count animals. It's absolutely fascinating. We've done it with narwhals in Canada. With the amount of imagery we have over time, we can monitor their habitats. You always hear the stories, this population is dying. We can count that and check it and turn it into real ground truth, real fact. So we're looking for these use cases because this is new technology at a global scale. What can we use it for? We're getting really close, up close imagery where each pixel is about 30 centimeters. We understand what's happening on our planet. The observation and the crunching of these massive chunks of data. So we have 125 petabytes of imagery that we store and process, and we add to every day. I think it's 3.5 million square kilometers of imagery every day of the Earth, and we pull it in and we process it. We can run algorithms that say, hey, actually this corner of this place, it's going to be a drought in the next 5 years. That's information that's invaluable for either these companies or these nonprofits that want to help.
Here we have a map that shows SAIL, the Surface Atmosphere Integrated Field Lab, focused really in the Colorado Rocky Mountains. And it's a big watershed. It's got the Continental Divide and that means a lot of people depend on it for water. It's a big area. They're using these satellites, but the satellites alone aren't enough to get verified data and to really see the big picture. That's something called ground truth.
Yeah, we definitely need ground control points so that you can verify on the ground, as you said, ground truthing the data from space to show that they're in the right place on the ground. That's really essential for any kind of scientific data like this.
We've made it to sunny Crested Butte, Colorado. We're about to head to the top of the mountain and check out one of Sail's observation towers. They're using more than 50 sensors, taking measurements from bedrock to satellites in space. Let's go see how it works.
Water is life, and it's something that we rely on, and a lot of our ecosystems rely on as well. We're here in the headwaters of the Colorado River, the major river system of the western United States. It serves about 40 million people, and the water for that river comes from snow that we're seeing here in the mountains. We're getting a lot less of it. We're here to make some very detailed measurements of how that change is occurring. So we are midway up the mountain on Crested Butte Mountain Resort. We are at the mountain site of the Surface Atmosphere Integrated Field Laboratory, or SAIL campaign. So we can learn a whole lot about the Earth from space. I have had the privilege of working with a lot of satellite instrument data sets, and it's really remarkable because they're so powerful. One instrument smaller than this trailer is able to measure the entire planet. At the same time, the ways that we measure snow is from satellite. That's actually a real cutting-edge problem, something that NASA is definitely still working on. We're providing a great set of observations to help inform a number of the researchers on SAIL who are thinking about how to design what that satellite looks like. And the reason it's so hard is because just looking at where snow is doesn't tell you the whole story.
It's such a complex problem, and it's really about seeing the big picture from every different angle, from space to underground to 50 different sensors. And we're at one of the study sites. We've got a couple of them right here. Let's go take a closer look at the precipitation radar.
Inside that radome, that ping pong ball, is an antenna that spins around and sends out microwave energy at wavelengths about 3 centimeters. It's very sensitive to how much rain is falling or how much snow is falling. This instrument measures the input of water into watersheds that serve the Colorado River. My colleague Ken Williams will talk a lot more about water accounting and why that's such a big deal.
How are some of these instruments working in conjunction with satellite imagery or balloons going into the atmosphere and some of the other data points that you guys are collecting?
Absolutely. What we're going to be taking a look at is called the aerosol observing system, and what it's really trying to do is to measure the particulates in the atmosphere. You can see that deposition or that distribution of dust from things like balloon-based measurements, from fixed-wing aircraft, and from satellites as well. It's what we call variations in albedo. And so how white the snowpack is versus how dark the snowpack is really important in terms of how this melts out in the spring and how that meltwater finds its way to our local streams and rivers.
That is so cool. Dust is so small, but you can still see it from space.
That's absolutely true. It may be small, but it can have a really outsized impact on how snowpack and mountain snowpack behaves. And so this is the first place in the United States that allows us to link atmospheric processes, where, when, and how precipitation is falling and occurring, and how that precipitation finds its way into local streams, rivers, and into deep groundwater as well. The aerosol observing system. Let's go take a look at it.
Thank you. See, that's why you're the scientist. All right, let's look.
With the rise of climate change, increased stress on plants, we're actually really interested to understand how atmospheric processes play a role in delivering a critical element like nitrogen to these watersheds. Well, what that's really allows us to do is now to link satellite-based imagery from the Landsat satellite products to really look at the greenness of our forests, okay? And greenness is really a proxy for forest health. So we can go back over a decade of Landsat satellite data and look at how these forests are either increasing in their greenness or decreasing.
I've done field work measuring trees, and I spent a week measuring trees with a colleague, and we measured the width of every tree to give us a sense of how old it was and how much carbon it was storing. But we covered a very, very small amount of trees in our week there, where a satellite can cover the whole surface in that same amount of time, all of the Earth. And so they kind of work together though. We use the ground-based measurements to calibrate the satellites. We use the satellites to fill in the spaces and times that we didn't have ground-based measurements.
Wow, I can't even count how many sensors we've looked at already, but we've got miles to go before we sleep. And if the weather's good, we might even be able to launch a balloon this afternoon. Let's pop the skis back on and do it.
Let's get them on.
Here we go. Gothic, Colorado is a former mining town outside of Crested Butte that is now used for scientific research. And in the winter, it's only accessible by cross-country skiing. A few miles later, we arrived at the Gothic Research Center. So this is really cool. We're able to see from space pretty much where we're standing right now. I mean, you can almost see us right there.
Yeah, right?
Not quite, but...
Well, you know, if we put our hands out, maybe, you know?
The satellites are giving context to all the sensors and work being done on the ground. And just like there's sensors here on Earth, there's also sensors up on those satellites.
Absolutely. So what we're seeing here is we're seeing in these imagery where the extent of where the snow is. But that doesn't actually tell us how much water is in there. And so a lot of the measurements here are getting at those details of how much water is in the snow that we're seeing here in the imagery. We are looking at the imagery that was collected today of an instrument called MODIS, which stands for the Moderate Resolution Imaging Spectroradiometer, so kind of a mouthful. This is on the NASA Worldview website that shows all kinds of imagery. It's super powerful. We know it's from today because we can see this black spot here is where the satellite data hasn't actually collected information yet.
What's at stake with these measurements?
It's what's at stake is the development of a predictive capability for how much water we're going to have in the future. We would really like to know if there's going to be enough water for all of us this year, next year, 5 years from now, 10 years from now. Without really going to these places and seeing what's actually happening on the ground, we're not able to know if any of our predictions have value.
We're getting ready to do the balloon launch. What exactly do you do to get ready and launch the balloon?
First, we prep a sonde, and this is one of your sondes here. We use this computer software here to condition this, and we basically calibrate it. So it has a relative humidity. We compare this sensor in here to a sensor inside here. Same thing with temperature.
And you make sure it's accurate.
Exactly.
Okay.
Yeah.
And the balloon is kind of just the vessel to bring it. How high exactly do these balloons go?
Say 90,000 feet. It sends via a radio link every second.
Okay.
So we get a download of height, temperature, relative humidity, and location, and it gives you some wind.
So we've got our helium balloon and a bunch of sensors. Yep. Going way, way up.
Yep.
All right, here we go. Launching. The weather balloon will rise into the mesosphere about 17 miles high, whereas the commonly agreed definition of space is around 62 miles high. Together, measurements from the weather balloon, the satellites, and all of the other sensors will help the sail team learn more about mountain watersheds. Water is life, and snow is life too for the 60 to 90% of people worldwide that depend on mountain watersheds for their water. We've made our way down to the Slate River, one of the tributaries to the Colorado. And even within the US, that's 40 million people that rely on this water. Now it turns out it's really hard to predict how much precipitation there's going to be in the mountains and how much of that's actually going to make its way into the river. And that's why SAIL is collecting an unprecedented amount of data from satellites orbiting right now all the way to underground to try to understand and actually predict the future. How much water will be here in 5 years? And that's a really important problem to solve.
This chart shows the increase in the number of operating satellites that exist right now. In 2006, there were less than 1,000. So fast forward to 2020, there were less than 3,500. And really, this number is going up exponentially with all the different satellites that are being launched, tiny little nanosatellites and smallsats, especially the ones for global internet services that are coming up.
We're continually thinking about what we're going to launch next, what we want to measure next, which science questions we need to answer. But we're also working at the same time to design what's called the Earth System Observatory. And this is a set of satellites that are going to work together to provide a 3D holistic picture of the Earth from the surface up through the atmosphere. The first satellite in that will be a satellite called NISAR. And NISAR is going to let us measure changes in the Earth's surface at a fine level so that we'll be able to see things like ice sheet collapse and landslides. Satellites are really critical because they provide us continuous observations and they provide a large extent. So many of our satellites are global in scope, so we see the whole Earth, not just the area right in front of us. And that's really important because climate and earth science, it's a global research area. And so the more we know about the entire Earth, the better we can understand Earth and the better we can think about how it might evolve in the future. And the satellites that we're designing and planning to launch in the future will provide even more information and give us a better sense of where we are and where we might go. So our data is, people use it around the world, from scientists to decision makers. And a lot of what we do when we're thinking about future missions is think about what questions do we have? What do we want to know about the Earth? And work from there to design a mission that can help answer that. So we know more than we ever have before. And every year we learn more. We keep developing new technologies and sensors that'll give us the ability to understand even more about the Earth, from heights of trees to how much snow to sea level rise, changes in ice sheets, carbon dioxide. So we know so much about the Earth, and the more we learn about the Earth and the more we understand the processes that affect it, the better we can plan for the future.
Now we're looking at a map of satellites in orbit. There's over 19,000, and if you scroll around, you can kind of see, they kind of look like they're everywhere, right? And then you zoom in, lower Earth orbit, there's even more. So they're at different altitudes, they're at different orbits, they're all spinning at once.
This is the live map that shows where they really are, and you can see the concentration in low Earth orbit.
And what's interesting is if you flip the type to junk, it turns out over 13,000 of those 19,000 are not operational. They're junk, they're old, they're not being used anymore. The not junk is only 5,000, so there's way more junk satellites up there than operating satellites. And if you play that out, you know, over time, there's just going to be more junk, and you know, it raises these questions. How do you get rid of them safely? How do you avoid collisions? You know, when two objects collide in orbit, it creates thousands of small pieces, and all of those small pieces can then collide again with other objects in space. So the worst case scenario with space debris is that you kind of create a belt of space debris all around Earth, and that makes it pretty hard to leave orbit. So it kind of shows how serious this all can be. Thankfully, there are some companies today starting to work on that.
My name is Eric Ingram. I'm co-founder and CEO of Scout, and we're a company developing space domain awareness and vision capabilities for satellites to be able to navigate autonomously, so essentially by themselves. So the way we currently track things in space, be it satellites or debris, is primarily with Earth ground-based radars and telescopes that track the traffic going overhead in space to determine which dot is which satellite. As the number of satellites up there increases, that becomes more difficult. So what we want to do is be able to better track all of that to, again, make space a safer place to operate in. The cost of getting to space and the cost of all the technology is decreasing, and the capability of that technology is increasing. Just like your cell phone can do a lot more now today than it could 10 years ago. And the same thing is true with satellites. You see Earth observation, communication satellites, internet providing satellites all going up in the near future, and that's changing the way space is operated in. And so there's a lot more satellites up there that are using space to get all of these amazing services down to Earth. And companies like ours are working to make sure the space traffic is navigating in a safe way and that everybody's able to use space to provide these services to Earth.
Not all satellites have fuel on board to move, and so who has the right of way? What happened on the roads, and then the seas, and then the sky, we're going to see replicate in space. So as things get crowded, you have to pay attention to directing traffic. You need to pay attention to cleaning streets. So all of these are going to have analogs in space. It'll be a smaller scale at first, but everything is moving really fast. The commercial and government collaborations have created these companies like SpaceX, which are bringing business practices. I mean, now we can put things in space at volume to start really exploring the world and making second and third homes for humans. It's a really exciting time.
Space startups are filling in for services that weren't even possible a few years ago and are more necessary today than ever before.
More satellites and sensors in space provides us with more data than we've ever had before and more insights about the Earth. It also means that we need more infrastructure to support this increase in activity.